Good afternoon and welcome to this showcase webinar organised on behalf of the Natural Environment Research Council's Environmental Risks to Infrastructure Innovation Programme, or as many of you have come to know it, NERC's ERIIP programme. My name is Owen Jenkins of Syria, and our team here provides support to NERC in delivering this programme, particularly in terms of industry brokerage and dissemination. We have 5 speakers today, each of whom will speak on the topic of scour and/or river debris. When we last looked at the list of registrants, there were over 90 registered for today's meeting. They haven't all joined yet, but we're hoping that they will shortly. On that list, there were 25 infrastructure owners, both private and public sector, including several local authorities, 15 environmental regulators, who of course are also asset owners, 35 consultants, 10 contractors, 10 universities and other organisations concerned with research. Before we move on to the 5 presentations, I just wanted to explain how we're going to run the meeting. We have a question and answer session at the very end. However, we would ask you to submit your questions using the comment box throughout the afternoon, but please state clearly which of the speakers you're directing your questions at. At the end of the sessions, after the 5 speakers have presented, we'll then try and select a cross-section of questions across the 5 speakers at the end. Because it's likely that there'll be a large number of questions for the 5 presentations, we may not have time to answer every single question, but we may also consider circulating a further selection of questions to the relevant speaker after the event, invite them to respond offline, and publish them on the ERIIP site at a later date. So that's all I wanted to make in terms of an introduction. So without further ado, I'd like to hand over control to Rob Lamb of the JBA Trust, who will be talking about a project he did in association with the University of Bristol, Uncertainty in Scour Risk Assessment and Elicitation of Expert Judgments. So over to you, Rob.
Thank you very much, Owen. Thank you very much, Owen, and good afternoon, everyone. Yes, thanks for that introduction. I'm Director of the JBA Trust, which is a not-for-profit foundation for knowledge exchange and training funded by the JBA Group companies, and also a professor in practice at Lancaster University, hence the logos on my title screen. I was asked to offer an industry perspective this afternoon. I wouldn't care to attempt to provide a definitive summary of all possible viewpoints from industry. So rather than trying to do the impossible, I'm going to talk instead about a project that we carried out starting in 2015 in conjunction with Bristol University. I just want to acknowledge here the collaborators Willie Aspinall, Henry Odbert and Torsten Wagner. This work was published last year in the journal Natural Hazards and Earth System Science in a paper that is open access, so you can download that freely, and also accompanied by a more detailed technical report that we published on our JBA Trust website. And the reason I want to talk about this study is because our objective here was broadly to explore what we could learn from expert judgments about scour risk assessments, and in particular about the uncertainties in scour risk assessments. So our initial premise here, well, it's twofold. The first part of this is that we contend that scour risk assessments are inherently uncertain, and there are numerous reasons for that uncertainty. One of the main causes of uncertainty is that the events that trigger scour damage and scour collapse in bridges are themselves somewhat unpredictable. So I'm thinking here in particular about bridge crossings over rivers, and therefore thinking about flood events, peak flows, and also things like debris and the recruitment, entrainments, and occurrence of blockage, which appear as somewhat stochastic processes. A second source of uncertainty, of course, then is that our knowledge, our ability to measure physical parameters and processes and model them empirically with physical models is also subject to some uncertainty. The second aspect of our initial premise was that uncertainty manifests itself in what we can see as a residual risk of bridge failures. So despite the very comprehensive protocols and actions taken to mitigate scour risk on an ongoing basis, structural failures and even collapse of bridges do still occur. An example here is some data from the British Railway Network. This is a database of historical railway bridge failures that we published in 2014. So it covers the history between 1846 and 2013, where there have been around 100 documented failures of rail bridges due to scour. And for many of those events, we've been able to reconstruct the hydrological conditions associated with those failures. So two things to note from this. One is that failures have occurred even during the relatively recent past, when we have had, the industry has had well developed and mature risk mitigation measures in place. And secondly, the trigger events, if you like, the magnitude of the event expressed in terms of the return period of the flood is very variable across those failure events. So there's some uncertainty clearly about how we would in fact predict a vulnerability to scour failure. So why did we adopt the form of expert elicitation study that we carried out? Well, the situation I've just described, I think, is that we have in bridge scour, we have a well-studied problem. There are many empirical studies, there are many data sets, there are numerous empirical models published on the topic, and yet for the reasons I've just tried to outline, we would contend that risk assessments remain uncertain. And this is exactly the kind of situation where we have both a depth of expert knowledge and also a high level of residual risk and uncertainty, where expert judgment has been found to offer a useful alternative perspective in addition to quantitative studies. So the methodology that we adopted, it was a statistically robust elicitation methodology. It was developed by Roger Cook at TU Delft in the Netherlands, and has been applied to date in many studies, well over 80 expert elicitation studies across a range of fields, including things like nuclear safety, climate change, biological hazards, and so on. And key elements of Cook's methodology are that the judgments of a group of experts are pooled, and that pooling process, that averaging, helps to encourage robustness in the elicitation results. And secondly, very importantly, individual experts' judgments within the process are weighted based on what can best be described as a form of calibration process. That calibration process works in two ways. To some extent, it weights experts based on how well they answer questions that are broadly similar to the questions that are the topic of the study, and as to how accurate their answers are. But it also crucially looks at how good those experts are at judging uncertainty when they're not sure of the true answer to a question. Our study involved 19 experts drawn primarily from industry, so 14 of them were from industry or regulatory organisations. 5 of them were academic researchers, although I think almost all of those academics had also worked within an industry context in one way or another. So from that point of view, to some extent, this does represent, I think, an industry perspective. It's also an international perspective. So we had a group of experts drawn from countries in which there are mature scour risk management processes in place. So the motivating question on a technical basis was essentially what should a Scour fragility function look like? So we imagined some kind of function that looks a bit like the graph on the screen, where we have a probability of bridge collapse due to Scour dependent on some load variable. So the first sort of technical question for the experts then was essentially what should that load variable be? Then we want to know what the curve itself should look like. So how would it be parameterized? What shape should it have? And finally, and something that's perhaps sometimes overlooked, is an assessment of the uncertainty about such a function. So what could our confidence be in a fragility function for Scour? So through the elicitation process, we asked our experts about a wide range of potential risk factors that could be used as loading conditions in a fragility analysis. We looked both at piers and abutments to check for any differences that might be relevant for the two different elements of a structure. Broadly speaking, the top 6 ranked factors in terms of importance that we got from the expert group are those shown on the slide here. So most of those, I think, would not be a surprise. We have information relating to the history of Scour, the watercourse characteristics, the nature of the bridge. I suppose 2 things I would pick out here that were emphasized in this part of the study were the understanding of the broad hydromorphological context for a bridge. So not just an analysis of the hydraulics and the morphology at the structure or very near to it, but also treating the watercourse and its structures as a whole system, and thinking about things like the removal of weirs or the installation of flood defences, even some distance from the bridge, if those might have an effect on that regime. The second thing that was emerged as being quite important that I would draw attention to here was considering recent flood history, and in particular the occurrence of sequences of events that could cause cumulative Scour damage. So from that part of the study, we then moved on to ask our experts to make some numerical judgments about failure probabilities. We gave them a set of idealized bridge and watercourse types and a series of idealized assumptions, scenarios for risk assessment and mitigation protocols. And I can't show all of those results in one slide. They're in the paper, but just to pick one of them out here, the graph at the top left, this is showing our experts' judgments about what a fragility function could look like for a bridge with deep or as it was termed, modern foundations in a relatively stable watercourse. And a couple of things to pick out from this. We asked them to assess failure probabilities for 3 potential loading conditions. Those were 25-year to 500-year floods, and also to give us estimates of 90% confidence intervals around those failure probabilities. And clearly what you can see from the graph is that the experts indicated a very wide range of uncertainty about those failure probabilities. What they didn't know when we did the study was that we had also done some statistical analysis on the railway bridge failure data, which gives us some kind of benchmark here. And that statistical analysis is shown in red on the graphs, and actually shows some consistency, I think, with the expert judgments, but a rather narrower range of uncertainties. So this does suggest that just looking purely at empirical data of failures can give us something useful, but may underestimate the real uncertainty around a Scour failure model. It's also interesting to see that although our experts stressed repeatedly during the study the importance of risk mitigation and risk assessment protocols, actually those the assumption of zero investment in mitigation and risk assessment didn't change their analysis of failure probabilities by as much as we thought it might. And I think there's a few implications for that. So to briefly cover the conclusions, we felt that our experts' views on potential risk factors for Scour were broadly consistent with industry practice, but they did perhaps emphasise the importance of sequences of flood events and the broader hydromorphological regime of a watercourse as being important. And there's a need there to think about suitable metrics that could reflect those factors within a risk assessment protocol. They also, as I said, identified very wide uncertainties about failure probabilities, and they did that even after accounting for the presence of investments in risk mitigation and risk assessment. And I think, if anything, that really just underlines the need for us to continue developing more comprehensive monitoring and assessment methods to try to constrain those uncertainties. And to me, that's the kind of thing that I think I'm hoping that we'll hear about in talks and in the rest of this webinar. And I very much look forward to seeing the following talks. So I'll finish there. Thank you very much.
Thank you very much, Rob, for an interesting talk. The next presenter will be Richard Williams at the University of Glasgow. So we'll be handing over control of the screen to you shortly. And the title of your talk will be Decision Support Frameworks to Incorporate Riverbank Stability in Pipeline Crossing Risks.
Thank you, Owen, and I think this presentation will tie quite nicely into where Rob Lamb just finished there, talking about the development of novel assessment methods. So the presentation that I'll be giving today presents output from the Natural Environmental Research Council ERIIP project that was awarded to myself and my co-investigator Trevor Hoy, and I'd also like to acknowledge John Maniatis, who was the research assistant on that project, and also Will Carroll and John Hicks at Scottish Water. Just a very quick overview of the ERIIP programme. There were three major themes for research grants within the ERIIP programme. The presentation I'm going to give you today addresses theme one, identifying, understanding and quantifying environmental risk to an infrastructure system, and also theme three, dealing with uncertainty, particularly how we deal with uncertainty with respect to making asset management decisions. So I'll be talking today about the development of a protocol for Scottish Water's asset management of pipeline crossings. Within the context of managing pipeline crossings, there are some broad management challenges that really cross across the whole infrastructure sector. Here in the UK, our ageing infrastructure and the associated challenges with that, extreme weather events, but also the development of novel information communication technology, the emergence of electronic asset management databases, often enabling asset inspectors to acquire data in the field using ruggedized tablet computers, acquiring georeferenced images, and also entering free text or making choices in drop-down boxes within those asset management platforms. And really the emergence of those mobile data collection methodologies, there was an opportunity that we identified to help Scottish Water to develop their protocol for collecting information on the stability of rivers at their pipeline crossings, and then to think about how the data that could actually be acquired by asset inspectors could be used to develop tools to actually prioritise repeat inspections. So Scottish Water provides water and wastewater services to 2.5 million homes in Scotland, 156,000 business properties. They've got an extensive pipe crossing network. Their drinking water network is 48,000 kilometres long. Their wastewater pipe network is 51,000 kilometres long. And it's river crossings within that network that are essentially some of the most vulnerable nodes. They're at risk both from vertical scour, but also lateral bank erosion. It's the latter, it's the horizontal movement of rivers that I'm going to be focusing upon in my talk today, rather than the vertical scour of a river bed. We're we're thinking about the actual movement of the channels to the left or right across the floodplain and what that might mean for pipeline crossing structures. On the right-hand side there, you can just see a map of where all those pipeline crossings are positioned within Scotland, where the population is densest across the central belt. We see that high density of crossings, but those pipe crossings really are distributed right across the Scottish mainland and the associated islands. I'm a fluvial geomorphologist, and the first thing to note is that in Scotland, as elsewhere, there's an incredible diversity of river environments. In upland areas, crossings might be in boulder bed or bedrock reaches. Further downstream, we might have a fluvial geomorphology that's predominantly characterized by actively meandering reaches. Some of those reaches might be natural. Some of those banks might actually have protection. Those rivers might have been straightened. There might be cohesive bank materials such as clays, or we might have alluvial gravels, sand and cobbles that make up the bank substrate. So all of those crossings that we saw in the last slide actually cross over a whole variety of different styles of rivers, which adds to the complexity of actually scoring the risk associated with each of those crossings from a river stability perspective. So when we started this project, we had a look at bridge scour assessment manuals, which tend to focus upon vertical scour rather than lateral erosion, and also often characterize risk assessment frameworks for transport bridges or bridges with abutments rather than pipeline crossings, which often span right the way across the river, and the concrete structures are often set back on top of the banks, enabling the river sometimes to actually be able to erode on the outer banks immediately vertically beneath the structure. And you can see that on example 3 on the image on the right hand side of the screen just now. Scottish Water observed that 30% of their pipeline crossings with observed riverbank instability are associated with either leaks or damaged foundations in their initial wave of asset inspections. Asset inspectors on the ground often aren't formally trained fluvial geomorphologists. So when we were thinking about how we would design our asset inspection protocol, we needed to think about the type of data that could be collected in the field without expert knowledge on river sedimentology and river channel change and associated hydraulics, but that could be interpreted in the field by asset inspectors or subsequently used further down the line by fluvial geomorphologists for a desk-based assessment exercise. I'd really like to just emphasize that a single interruption within the network can sometimes cost up to tens of millions of pounds. Some of these crossings are in very remote areas, and extensive roading is needed to actually bring heavy machinery onto site to actually mend the network. So Scottish Water were very keen as they updated their asset management protocols to think about essentially to some extent an unknown in terms of how data could actually be collected on these crossings. So the aim of our project was to develop a decision support network to direct further desk-based assessment of river stability, to identify the need for scour or bank protection measures, and to importantly establish the frequency of repeat asset inspections for individual sites. I'm going to talk about a number of methodological steps in the rest of my presentation. I'm first going to just briefly review bank erosion susceptibility indices and what was out there for us to build upon, to talk about how we enhance the asset inspection protocol that's already being used by Scottish Water. We're going to talk about our development and testing of a specific erosion risk index that could be adopted by Scottish Water, and finally to identify actions that could be taken based on the ERIIP scores that were calculated. As I mentioned earlier, I'm a fluvial geomorphologist. In fluvial geomorphology, a whole range of different approaches have been taken to characterize the geomorphology and the stability of rivers. Things like Angela Gannell's Morph framework, Gary Briley's river styles, Tim Beach's natural channel classification approaches are all widely used by fluvial geomorphologists, but they often require extensive information about a river catchment upstream and downstream of a crossing, and also considerable survey data in the reach that's actually of interest. So we tried to find existing approaches that could be used to score bank erosion at a particular site. A review was completed by Connell in 2012, and on the slide here you can see three techniques, three indices: a bank erosion susceptibility index, a bank erosion hazard index, and a bank erosion potential index that have all been developed, but all of which requires relatively high degree of input data to actually calculate those indices. For example, actually measuring the angle of a bank, actually using quadrat surveys to measure the distribution of vegetation, measuring root density, riparian diversity, bank material, etc. So we decided that we need to develop a simpler index that could use data that could be quite quickly acquired by an asset inspector within 10 or 15 minutes of arriving on site. Initially, Scottish Water, when they started to use their mobile app to acquire data at their pipeline crossings, a lot of the photos were looking and focused upon the structural elements of the river crossing itself, and it proved that to actually assess the geomorphology of the river upstream and downstream of the crossing, as well as immediately below the crossing, we needed to change the guidance that was given to asset inspectors to actually make sure they were positioning themselves to acquire photographic coverage of the river on the left and right banks, both upstream and downstream of the pipeline crossing, as well as immediately beneath the crossing. And this is extracted from a report that we developed, actually showing the inspectors where they should be taking images, so that we could then develop a protocol to assess the coverage of vegetation, for example, and assess any evidence of bank erosion across that section from 5 widths upstream to 5 widths downstream, to identify whether the crossing was at risk from bank instability. Following the update of the app that was being used by asset inspectors, we developed and identified 6 variables that could go into a scoring system to calculate an erosion risk index for every single pipeline crossing. And this slide just shows those 6 variables. We're identifying whether there's active bank erosion beneath the crossing, whether there's active bank erosion upstream or downstream of the crossing, whether bank protection exists beneath the crossing and upstream or downstream of the crossing. We're identifying the bank angle, and we're also identifying the presence or absence of vegetation on the basis that vegetation offers resistance against active bank erosion. For each of these variables, we developed a scale ranging from 0 through to 5, which was compatible with Scottish Water's existing system, and you developed a procedure for asset inspectors in the office to actually then look at the photographic evidence and rate score each of these variables on this rating from 0 to 5. The rest of our project work then focused upon actually testing a framework to actually first determine the calculation method to actually calculate the erosion risk index and assess whether it correctly identified high-risk sites, and then to look at whether there was user bias between people that were actually undertaking the scoring, and then to look at whether there was consistency in the methodology between both inspections undertaken by the asset managers at Scottish Water who were desk-based, and by experienced geomorphologists as part of our research group at the University of Glasgow, and also from site visits to actually assess the susceptibility on site rather than using the photographic evidence. We tried 4 different calculation methods for the erosion risk index, including a probabilistic weighted index, a weighted addition approach, a simple multiplication approach, and a weighted scaled mean. And it was that latter weighted scaled mean that performed best at discriminating between different degrees of bank erosion at different sites. And we also added a data quality element to that ERI score to ensure that where photographic evidence wasn't available, perhaps because of high vegetation or for missing photos, the resulting ERI score would be sufficiently low to prompt resurvey. So I'm just going to show 3 or 4 charts now before summarizing, just to show the results from that testing. This chart shows the first step of testing. We're testing 13 sites that were identified by Scottish Water that were particularly susceptible to bank erosion. They were identified from a keyword search of the existing asset information database. These are the resulting erosion risk index that were calculated. All of those indices were above 3, which meant that the scoring system gave us confidence in using that weighted scaled mean to actually identify those assets that were most susceptible to bank erosion. We'd expect those all to fall in the 3, 4, or 5 category. Next, we're particularly interested in user bias. So we devised a method where we tested 31 sites, 3 asset assessors at Scottish Water and George Maniatis at University of Glasgow independently used the workflow to calculate the erosion risk index at each of these sites. From the results, we can see that there's general convergence of results at particular sites, often agreement where there are data quality issues, and a lot of those data quality issues were images that were taken in the summer when the vegetation was too high, or images that didn't show the full extent of the banks upstream and downstream. Our final testing looked at the consistency of the methodology with field inspections. Several of us travelled to the Outer Hebrides and applied the erosion risk index methodology on site. At the same time, Scottish Water blindly calculated the erosion risk index at each of these sites for these 23 crossings. The desk-based assessment overscored 14 of the 23 sites. 4 sites had the same score, and 1 site scored higher in field assessment. So if anything, the desk-based assessment is overscoring rather than underscoring, which is the direction that we would want this to be in. Our final component of testing was to select 118 random sites from the 1,500 in the database. 69 of those sites agreed between the desk-based assessment by Scottish Water and the desk-based University of Glasgow researcher assessment. 25 sites had data quality issues, and there wasn't a systematic bias for the sites where there was a difference. The 24 sites where there's a difference of 1 in the scores. There wasn't a bias linked into the severity of bank erosion. So the final step was to provide guidance on next steps. So based on those erosion risk scores that Scottish Water are now calculating for all of their pipeline crossings, we decided the next steps, whether repeat inspections should be immediate for cases with severe ongoing bank erosion, or whether for sites with 3, for example, a routine resurvey is fine. For sites that were scored at 1 or 2, resurvey can be infrequent unless there are significant changes upstream, such as river restoration or major in-channel works that might cause the instability within the river reaches. So I'd just like to finish with a note about our ERIIP project, which also enabled us to visit the Philippines and Indonesia and think about bank stability at these sites. A lot of rivers in the UK are relatively stable, but if we travel to other parts of the world, some relatively frequent floods can cause significant riverbank changes. So the map on the left-hand side of the screen here is showing change within 3 years and huge volumes of sediment changing. So hopefully the system that we've been using and developing in partnership with Scottish Water will also have relevance to other pipeline managers and infrastructure owners here in the UK, but also further afield. So I'll leave you with those conclusions on the screen, as I think I'm just out of time, and we'll just conclude that Scottish Water are currently implementing this scoring system within their live data capture app. So thank you very much.
Thank you very much, Richard. And just a reminder to all the delegates, please keep your questions coming in, but just be clear who you're asking the questions of. The next presentation, we're going across to the University of Strathclyde to Daniel Zonta, and his presentation will be early warning decision support systems for the management of underwater scour risk for road and railway bridges. So control coming across to you now, Daniel.
Okay, thank you very much, Owen. So in the next 15 minutes, I would like to introduce you the rationale of a NERC project related to management of underwater scouring for road and railway bridges. This is a project that involved the University of Strathclyde, the University of ERIIP, and also involved the two largest transport operators in Scotland, which are Transport Scotland and Metrorail. It also involved the Scottish Environmental Protection Agency, SEPA, and ERIIP. Rob Lamb have already clarified that flood-induced scour is the leading cause of bridge failure in the UK and also in the rest of the world. In the UK, in the period 1846-2013, 138 bridge failures have been recorded, while in the US we had more than 800 core failures in the period in the last 50 years, which means basically 22 failure per year on average due to scour. If we look at Scotland alone, Transport Scotland operates more than 2,000 bridges. Of those, 160 are in need of monitoring and scour protection measures. And as for Metrorail, Metrorail managing Scotland 1,750 bridges, and 58 of them are considered to be susceptible to scour. Most importantly, we expect that the trend of scour failure is going to increase in the future due to the climate change. And what is exactly scour and how does it affect the stability of bridges? Well, we all are acquainted with the scour mechanism. We know that river naturally transport sediment, and the sediment transportation occurs when the flow velocity exceeds the critical velocity because of a flood event or because of variation in the channel geometry of the bridge because of friction. So the local increase of velocity produce locally a removal of sediment, what we call scour. And bridge overpass a river are often some piers in the riverbed, and the pier foundation very often, especially for old bridge, lay directly on the riverbed. So scour results in the removal of the bed material around the bridge foundation, and as long as the scour grows, this may jeopardize the stability of the bridge and ultimately produce the collapse of the bridge. So example of bridge collapse occurred that has occurred in the UK and in Ireland in the recent time include the Granite Bridge in Wales in '87, the Northside Bridge in Cumbria in 2009, the Malahide Viaduct in Dublin in 2010, and most recently the Leamington Viaduct in Scotland in 2015. So it is fundamental to us to understand what is the scour depth in order to prevent the possible scour failure in our bridge network. So how can we prevent and how can we assess the depth of the scour? The simpler method, the simpler approach is try to estimate a priori what is the scour depth with analytical methods. In addition, we can use a visual inspection for directly assessing the scour depth, or we can use monitoring system to do the same. For example, Transport Scotland and Metrorail use their own procedure to calculate analytically what may be the cow depth following to an extreme event. And these procedures are, for instance, the BD 9712 for Transport Scotland and the EX 2502 for Metrorail. Both of the procedures are ultimately based on the SEER recommendation for cow evaluation and include the two levels of assessment. At the first level, the logic is to identify those tractors which are susceptible to scour and those that can be excluded for scour risk. At the second level, for those tractors that are susceptible for scour, there is a formal calculation of the possible scour depth that has to be compared with the foundation level. So, of course, this calculation is very uncertain and is based on a number of information of the ridge geometry and on the flood event and the riverbed. So typically the information that feed this model at the water level and the grain size of our riverbed, and based on that we try to understand, try to make an estimation a priori of what is the cow depth D. Of course, this estimation, as Rob Lambert has clearly reminded in his first presentation, undergoes a very, very strong uncertainty, and this model has inevitably a big error of estimation. And so this estimation, what can we do to improve this estimation? Of course, the Transportation Agency typically resorts to visual inspection, and for those bridges that are really susceptible to scour, Transport Agency routinely inspect their assets for scour, but this scour require underwater or dive inspection. Now, an underwater inspection is has some drawbacks. First of all, they are very expensive. They're also very time-consuming, and most importantly, they cannot be carried out during a flood event because of safety reasons. So, Transport Scotland, for example, currently spend something in the order of 2 million per annum on routine inspection of bridges, while Metrorail in Scotland alone spend 0.4 million per annum either. An alternative to direct visual inspection of car is a monitoring system. For example, this picture shows a Python core monitoring system developed at the University of Tatlide. It is based on a commercial soil monitor sensor, and it consists in a sensing rod equipped with an electromagnetic sensor into a protective tube. Basically, this sensor detects the magnetic permeability of the soil, or the electrical permittivity of the soil surrounding the sensor, and allow to separate the soil media, the water, and the soil deposition. So in principle, we could think to install one of the sensors at each pier site in order to detect in real time what is the scour level. The only problem is here that this operation monitoring all the pier of all the bridge of stock is not economically sustainable. So the objective of our project is to develop a scour hazard model which is able to estimate the scour level at different locations, taking advantage of real-time information for scour monitoring system. But the rationale here is let's install the monitoring system only on a limited number of critical locations, and then let's use a probabilistic approach based on Bayesian network to extend, to project this information either to a monitoring bridge and piers. So what is the rationale of this approach? Okay, we have seen that if we want to predict a priori what is the cow level based on the water level and the knowledge of the approximate knowledge of the grain size, we need to use a prediction model, which is typically what the Transportation Agency normally do. And imagine that we have a bridge with the two piers into the riverbed. D1 and D2 are the two scour level that we are expecting to get. So in the same way as we can estimate the scour depth at one of the piers, we can apply the same procedure to estimate the scour at the other piers, because the two quantity are correlated in the water level and the grain size, and also in the error that is involved into the model, with some kind of correlation between these two quantities. Now, imagine that we install a monitoring system on one of the two piers. So in this case, during a flooding event, we can measure directly the depth of the scour. So we don't have an uncertainty anymore. We have a deterministic value of scour level. Now, with this information, we can use this information to update the parent variable, the input variable that we're using for this model, the water level, the grain size, and more importantly, the correlated error of the model. And using this updated variable, we can recalculate the second scour level that in this case will provide a different value, but most importantly, a much smaller uncertainty. So the logic is if we observe if we have two piers on the same bridge and we observe one of the two, we can have a much better estimation of the other pier, even if we don't install a monitoring system directly on the other piers. So we can extend this logic to any bridge stock by highlighting what are the variables that allow to correlate the model to predict the scour. So this logical correlation is embedded in this model that we call a Bayesian network. Let's see what happened if we apply this on a real-world case study. So for this project, we investigated in particularly pilot network consisting of 3 bridges that are managed by Transport Scotland. These 3 bridges are the A76-200 bridge near New Camnock, the Guido Bridge, and the Danscombe Bridge. They are all located in southwest Scotland over the same river, on the River Nith. So the fact that we are on the same river allows us to assume that there is a correlation in the riverbed sediment, and we will use this information to try to extend the information that we can get on one bridge to the other. So let's analyze the 3 case study. The first case study is a 3-span stone measuring arc bridge with 2 piers in the riverbed and with a superficial foundation. So this is a bridge that is used by Transport Scotland as a pilot monitoring, as a pilot site for testing the stackline monitoring system, and one of the 2 piers is going to be monitored with a sensing probe. So the second bridge is a 3-span stone measuring arc bridge with 1 pier in the riverbed. These bridges are being refurbished with a concrete deck, and the bed width is 21.4 meters. The third bridge, the Danscombe Bridge, is a 7-span concrete composite bridge with 1 pier in the riverbed. In this case, we have deep foundation. Okay, if we want to model the mutual correlation between the different quantities of these 3 bridges, we will end up with a Bayesian network similar to that shown into the picture. So in blue, we have highlighted here the information that we can assume a priori, for example, the flow during a flooding event, and in green are the quantity that we observe during the monitoring process. For example, we can observe here at the A76 bridge what is the actual scour level at one of the 2 piers. We can also observe a different location of the network, what is the water level. So using this information, we can back calculate, we can make a prediction using this network, and once we have some direct observation of the scour level, we can use the process showed before in order to recalculate the scour depth even in the location that are not directly monitored by a monitoring system. Okay, let's see what happened in a simulation. So let's use this model to try to predict what is the scour level for a particular event. So the prediction of the scour level is typically very, very uncertain. For example, in the case of the New Camnock Bridge, so we can expect for a particular event total scour depth in the order of 2 meters with a standard deviation of 0.7 meters, which is a very huge uncertainty. Okay, and similarly for the other bridge for the same event, we can expect a very, very large uncertainty in the scour estimation. Now, let's say that the New Camnock Bridge is monitored, as it actually is, with a monitoring system on one of its 2 piers. And this monitoring system records a total scour depth during the event of 0.45 meters, 45 centimeters. So, of course, for this particular pier, we know exactly what is the scour level. But what can we say, for example, for the nearby piers on the same bridge? If we back calculate the Bayesian network seen before, so we can update the distribution of what can be the actual Scour level on the other peer. And in average, we can guess that the total Scour depth in the other peer is in the same order, but with a larger uncertainty. So our estimation is 45 centimeters, for example, with a 20 centimeters of a standard deviation. And using the same network, by taking advantage of the correlation in the riverbed sediment, we can also try to guess probabilistically what is the Scour level in the other location. So, for example, for the Guido Bridge, the estimation show a total Scour level of 0.9 meter with a standard deviation of 25 centimeters, and for the Dartford Bridge, 79 centimeters of Scour with a 25 centimeters of standard deviation. What is most important in this approach is that we have, even if we are not monitoring directly the Scour level in this bridge, using the correlation with the other bridge, we are able to reduce the uncertainty of our estimation. So in conclusion, in principle, monitoring system would allow us to detect the Scour depth at any location, but clearly monitoring an entire bridge stock with all bridges, all piers is not economically sustainable for a transportation agency. So we proposed a system based on Bayesian network, which is able to estimate and understand the Scour depth for monitoring only a critical location, and when we observe a particular Scour realization on a particular location, we can spread this information across the network, and so we can apply the Scour depth with some uncertainty even in unmonitored bridges. So we demonstrated this approach on a case study of 3 bridges that are managed by Dartford Scotland in southern Scotland over the same river, and the observation for monitoring system increased the accuracy of our estimation even in the unmonitored bridge, and this increase in accuracy is in the order, in our example, of 70%. So this framework, of course, can be extended to any bridge stock of any size and for any transportation agency. I showed you very briefly what is the reference list for the information that we showed here in my presentation, and I thank you for your attention.
Thank you very much, Danielle. Next, we're heading south down to the University of Southampton with Gustavo de Almeida, and his presentation will be debris effects on bridge resilience and flooding. So you click on. Just making you a presenter now.
Okay. Hello, good afternoon, and thanks. My name is Gustavo de Almeida, and I'm the PI of this project, Debris Effects on Bridge Resilience and Flooding, which is a collaboration between the University of Southampton and HR Wallingford. I would like to acknowledge the contribution of my project collaborator, co-PI, Dr. Manuela Scaramella from HR. And the project has also Network Railway and Environment Agency as project partners. So the problem we are dealing with as part of this project is this issue of the accumulation of debris at bridge piers that occur during flood events. And it's a big issue that has led to the failure of many bridges around the world. And the problem can be essentially, from the point of view of assessment of risk or hazard, can be decomposed into 3 main effects driven by the accumulation of the debris. The first one is an increase in the lateral loadings, that is the drag force that is exerted by the debris and the flow onto the pier, that can be up to an order of magnitude higher than the drag force that is usually applied by the hydrodynamics on the pier alone. The second effect is what we call afflux, which is simply an increase in the upstream water levels due to the same drag force, but the reaction of that force exerted on the flow. Finally, the third one, which is probably the most important and has been already highlighted in this webinar, is the problem of scour. The presence of the debris will increase the flow velocities near the bed, and that drives an increase in the scour depth that has been reported relatively recently in the literature as up to 4 or 5 times larger than the scour without the debris. But we will review this information as part of this project. And finally, I would like to highlight that studies in the UK and the US estimate that about 1/3 of all bridge failures that occur around, mainly in the US and in the UK, are somehow related to the presence of debris accumulations. And this is a problem that involves a high level of uncertainty, as has already been mentioned here as well. But I think most of this uncertainty is because until recently, we didn't have a way to estimate or to have any guidance about what size or what dimensions these debris accumulations could reach during a flood event. And this has been addressed in one of our research here at the University of Southampton that has been going on for the last 4 years, where experiments like that has been conducted, where we try to understand the process of the formation of the debris accumulation itself, rather than just the effects of a given debris accumulation on scour or flux or whatever. So what these experiments have found by introducing debris and analyzing the process of the accumulation itself is that in all of these experiments, the debris fails, that is, the debris is removed by the flow from the bridge at a particular instant during the experiments, which it should be now. So this phenomenon usually occurs when the size of the accumulation is highest. And by performing many of these experiments, we managed to reach these curves here that represent these 3 variables characterizing the geometry of the debris accumulation, that is the width, the depth, and the length along the river as a function of flow variables, in this case, a Froude number, and also on the characteristics of the debris that is supplied to the channel. So summarizing these previous components of this research, these experiments, more than 800 experiments, now allow us to predict the worst case scenario given flow conditions and some characteristics of the channel and characteristics of the oncoming debris that is transported by the river. So this now allows us to provide a better assessment of those 3 components that I described before, because knowledge about the dimensions is key to assess each of those effects of debris accumulations on those 3 components. In particular, starting with the problem of lateral loadings, that is simply governed by a drag force relation. And the main unknown in this problem is the area, the blockage area, that is this variable here, and the coefficient of drag. If we know these 2 components, we can easily address the problem of lateral loading driven by debris. And this can now be assessed by these relations that we are providing for the width, the maximum width that accumulation can produce, and the depth of that accumulation for both natural debris and for debris composed of elements of just a single length. We have also, as part of these experiments, actually measured the forces that were being exerted on the piers. And these allowed us to derive an experimental value, empirical value for the drag coefficient of these very irregular and porous media, which is difficult to estimate only from theoretical considerations. So we now have we are able to provide an assessment for the drag coefficient as well, and we kind of close this problem of assessing lateral loadings on bridge pier. The second component, which is this problem of assessing scour driven by debris, has been studied before, but I think the main limitation of previous studies is that they had to assume a given dimensions and shape of the debris accumulation and perform experiments that would tell us how much debris is increased by the presence of the debris. This has led to estimations that were, let's say, up to 4 or 5 times the scour depth that would occur without the debris. Our experiments that were performed as part of this project that I'm showing here on this video, where you can clearly see that a higher scour depth occurring for the experiments with the debris relative to the scour without the debris. In these experiments, we used the more realistic dimensions for the debris accumulations from our previous experiments. And by doing that and repeating those experiments many times that were done by Dr. Francisco Cantero Chinchilla, which I have to acknowledge his collaboration as part of this project, this has led to curves like that, where we can compare the evolution in time of scours with and without the debris. And in this particular example, the increase in the scour depth is 40% compared to the experiments without the debris in place. So that is a lot less than previous experiments for this particular case, but here we have a more general overview of all of the experiments that he performed as part of this project. And on the top left-hand side of this figure, we see the experiments with the debris, and the right-hand side, we see the corresponding experiments without the debris. And we can clearly see that obviously the debris plays a major role in increasing the scour, and the lower figure actually shows the comparison. The x-axis here is the results of the time evolution of debris with without debris, and on this axis we observe the results with the debris in place. So what we can extract from this figure is that for these experiments, we covered a relatively wide range of dimensionless variables for this type of problems. The maximum scour depth was increased up to, let's say, 80% the scour depth that would have been predicted without the debris in place. So that is a lot less than previous experiments have shown, which suggests that these previous experiments would be overestimating the influence of debris on scour. And the reason why this overestimation has occurred is because these previous experiments had to assume particular shapes and dimensions of the debris blockages, which are unlikely to actually be formed because they would be removed by the flow before reaching those very large dimensions. So this provides further guidance to practitioners in estimating the influence of debris on the maximum scour depth that we can expect. A third element of the project was to develop a methodology or an improvement methodology to assess the influence of debris on afterlives. And this, again, is a problem that can be defined from a purely mechanicist perspective by conservation of momentum or conservation of energy. But one of the key components in these equations is the actual force that debris would exert on the flow. And that is linked again to this drag force, the drag force exerted by the debris accumulation, which depends on the size of the accumulation, which was the main unknown so far. So again, those experiments now allows us to perform a better assessment of this component of the equation, which will lead to more case-specific and hopefully more accurate predictions of afflux. The initial idea of this project was to incorporate this knowledge into the Environment Agency's afflux estimator, and that we worked together with HR Wallingford on this potential implementation. But during the project, they highlighted that the technologies have been developed almost 20 years ago, and they were finding it difficult to compile those source codes or even find parts of those source codes. So we ended up taking the decision to develop our own standalone version of a debris-induced afflux estimator, which we'll be making available as part of the project outcome. So this is a preliminary version of that software that will be made available online, where users can basically put some characteristics of the cross-section, characteristics of the bridge, choose some of the equations that will be used to determine the drag coefficient for the pier alone, for example, and the software will compute the dimensions of the debris accumulations that are likely, or the maximum or worst case scenario debris accumulations that can happen under those under this scenario, and given those dimensions, it will compute the drag force and also the afflux, which is shown here. In this particular case, is very small because of the characteristics of the cross-section and the flow conditions, but it can be a lot larger. So this software will be made available online again. And again, I need to acknowledge the very fantastic work done by Dr. Francisco Cantero in developing this software within the time limitations of this project. So to conclude this presentation, I would like to highlight that the outcomes of these projects somehow improve the tools available to assess these components that we see listed here. The first one being the assessment of the maximum dimensions of wood debris accumulations that can occur at particular bridge piers given flow and debris characteristics. Lateral loadings exerted by these accumulations on bridge piers, the increase in scour depth by the accumulation of these debris blockage, and finally the afflux, the increasing upstream water levels driven by these accumulations. Thank you very much, and I think we can move on to the next presenter.
Thank you very much, Gustavo. We're now heading west to the University of Exeter and Prakash Kripakran, who will be talking about assessing scour risk due to debris blockage. This particular project isn't one in the ERIIP series, but we thought it would still be very relevant to today. So I'll just hand over control to you. Yeah, that's okay. So you should be able to connect now, Prakash.
Yeah.
Thank you.
Yeah, okay. Thanks very much for giving me this opportunity. My name is Prakash Kripakran. I'm a senior lecturer at the University of Exeter. What I'm going to be doing is essentially present some results from an EPSRT project, which is in the final stretch now. So we are going to finish sometime in November, later this year. So as Owen mentioned, this is relevant to the topic, but not strictly within the ERIIP program as such, but it sort of nicely fits in with the previous talk given by Gustavo. It's very similar topics. We are also looking at debris, and particularly looking at debris-induced scour. Yeah, okay. So the project sort of came about on the back of conversations with a number of industry partners, Network Rail in particular. You may recognize the picture on the screen. And this is the bridge failure at Feltham. It was a masonry arch that failed in 2009. It was on the line to London, and it was suspected the failure was attributed to debris accumulation upstream of the abutment, and there was increasingly a cognizance that there was not sufficient guidance for assessing debris-induced bridge scour risks, and that the current guidance was not adequate for managing these risks. And so we led a proposal with Harriet-Ward University, University of Belgrade, and a number of industry partners who I'm not quoting here, but it includes Bridge Owners Forum, Adept, Jeremy Bunn Associates, Mark McDonald, a lot of people who were on the steering committee for the Syria C742 document, because this was put together pretty much at the same time the revision happened about 3-4 years ago now. So the main motivation was to understand the science behind the science describing the characteristics of flow, flow behavior around debris. We were particularly focusing on masonry bridges because I think debris accumulation is particularly serious in masonry bridges and bridge piers because they are chunkier, thicker. We are also looking at masonry arches in particular as well. So we are also looking at hydrodynamic effects on masonry arch abutments as well as on inundation. And a key part of the proposal was to take forward the findings and integrate it within an approach for assessing bridge risks to hydraulic action. And specifically, we are aiming to embed this within the C742 guidance in some form at a later stage. And so the project essentially consists of a number of laboratory experiments in the fluids lab we have here. We are also doing a lot of numerical modeling, CFD-based modeling, and eventually taking forward results from both into creation of a guidance. So in this presentation, I'm going to skim over the science bits. I'm not going to talk much about the experiments or the modeling. I'm going to focus more on the guidance bit, or what we are proposing to do. So just to give an idea of the kind of experiments we're doing, it's similar to what Gustavo mentioned. We are not simulating debris formation. We are actually using solid objects for debris. So we took our information based on publications in the US and in Europe, including the UK, where there have been extensive studies on how debris accumulates in structures just based on observations, purely based on data gathered on debris accumulation at structures. And we have done a number of experiments in the lab. We are particularly looking at low flow conditions. So we are not looking necessarily at flood conditions. So the Feltham Bridge failure, for example, was not during a flood alert. The failure happened when there was no flood alert. It was not really very high flow in the river, but the scour happened due to debris in that scenario. And so the kind of shapes we are using, this is sort of goes against what the previous presenter was saying in a way. We are using solid objects of different geometries. I think the previous presenter was referring to this geometry, a wedge-shaped geometry, which is most prevalent. But we also looked at tree logs as well as debris mats. So this is a rectangular kind of mat. So a lot of debris just piling up in front of the pier. And notably, we are using a wedge-shaped pier rather than a circular pier. We're using a wedge-shaped pier because we understand typical masonry piers tend to be rectangular with cutwaters at the two ends. So this is representative of a typical masonry bridge pier. And these are some of the dimensions that we've used. I'm not going to go into these in detail, but these are now published in a Journal of Hydraulic Research paper. So we also have done CFD modeling, like I mentioned. The purpose of the CFD modeling is essentially to validate some models using laboratory results, and then use the models to run for scenarios which are not possible to do in the laboratory. In the laboratory, we are constrained by limits on discharge that we can simulate in the flume, as well as constraints of scaling. But in the CFD, you can, on paper, run it at full scale, even though it's computationally intensive. In terms of time, it may be faster. So our goal is to actually take the laboratory results, calibrate a few CFD models using the data, and then use the CFD to extrapolate for a wide number of, wide range of scenarios. And we have calibrated our CFD models. This is just a picture showing that the CFD models free surface flow. We have done a two-phase simulation, including the free surface, and we're able to match free surface profiles, both from laboratory conditions and CFD. They are consistent. We are also able to match velocity data. So we have taken velocity data from the experimental setup. We are able to match it with CFD predictions, and it's surprisingly very close. So the CFD models are, come very close to predicting measured conditions, actually. And so we are able to use the CFD models to then go off and do simulations for a different number of scenarios, especially looking at debris geometry, looking at angle of attack, because most all the experiments we do in the lab are basically at, the pier is perfectly aligned with the channel. But we know that in real life, it's hardly the case. And we're also able to run at, with bigger blockages than we probably wanted to do in the flume because of wall effects coming into play. So I'm not going to focus, I've skimmed over that bit, but I think what is more interesting for you probably is what we want to do using the data. So our aim is to make an impact on the C742 guidance. I think for bridge engineers here, you may recognize the equation. That is the equation that is by Brussers, that is referred to in the C742. Currently, this is the equation that is used to predict Scour or estimate Scour. It consists of a term capital D, which is the pier width, times a number of factors to take into account different parameters, the shape of the pier, the flow depth, etc. So what is notable is that the equation doesn't explicitly account for debris effects directly. It doesn't have a factor that accounts for the increase in Scour due to debris. So what is instead done is the pier width is modified to something called an equivalent pier width. So instead of D, we put in a factor of just DE, and DE is the pier width that is computed based on some studies done by Melvin and Dongal in 1992. So it's in the paper referred to there, and they've done a number of experiments with a circular pier and debris accumulated around the top, as shown in the figure here. So it's a circular piece of debris around the pier, and they've derived the equations on the back of laboratory experiments using this kind of a scenario, and that is used to estimate DE. So the assumption here is that the effect of debris is primarily to increase the obstruction size, which can be accounted for by increasing the pier width. And the sort of the weaknesses here is that it doesn't really account for how long the debris is. So it doesn't account for how long the debris is stream-wise. It also doesn't give you it also doesn't allow you to assess how much the scour would be if the debris was at a different elevation. So if it was not at the top but was partially submerged, for example, or somewhere at the bottom. So from our experiments, we have done experiments of a number of scenarios. So we sort of identified the key parameters that actually govern scour depth or the scour depth primarily due to debris. And the factors that are related to the debris geometry are basically debris length. So here LB refers to debris length, which is the stream-wise length. And the other factor is the blockage area, is how much of the cross-section is blocked by debris, as well as the elevation of debris, which is the height from the riverbed to the bottom of the debris. So these, we believe, are the three main factors that are determining the amplification due to debris, the amplification in scour due to debris. Just to give some results, so this is a plot that shows the amplification in scour on the y-axis. So ds over ds0 is basically how much the scour is scour with debris is more than the scour without debris. On the y-axis, on the x-axis, what we have is the length of debris normalized to the pier width. What it basically tells you is that the maximum scour due to debris happens when the length of the debris is 3 times the pier width, roughly. So for the for LD over D equal to 3 approximately, that's when you get an amplification in scour of almost double the scour that you would see without debris. Similarly, we also looked at debris on the bed. So if the debris is on the bed, understandably it has a protective effect. So it tends to protect rather than cause more erosion. So depending upon the length of debris, you can have an enhancement in the protection effect. And similarly, if the length of the debris is 3 times the pier width, it sort of tapers off after that, the protection effects. So in effect, if the debris, if you have debris, you could potentially sink it to the bed if you want to lessen its effect. We've also similarly not just used our data, we've also used data from other studies. So we are not just using our external results. We understand there are results from other researchers around the world, Lagasse in the US, Pagliara from Italy, and so on. And we are trying to make sure our the equations or the relationships we put forward are consistent with data that we get from literature. And I think these are again other plots that illustrate the effects of the blockage ratio and the debris elevation. And I'm going to skim over these two because I think we are very close to the end of the session. So what we are essentially proposing as part of this research is to come up with a debris enhancement factor. So we are proposing to include an additional factor in the equation called phi debris, which would effectively tell you how much is the enhancement in scour solely due to debris. So currently we've got a relationship. We estimate this value based on the 3 parameters that I mentioned earlier, which is the debris length, debris blockage ratio, as well as debris elevation. So these are all sort of preliminary data. So this is not final, but we are in the process of coming up with a very simple way of estimating the phi debris factor here. And the idea would be that we are in the process of publishing it, so we will be able to show that the equation that we come up with tallies with data that we have. So for example, this is data for scour predicted versus scour measured, and the equation comes up with reliable estimates for a wide range of data points effectively. And so it is reliable metric to assess debris effects. So I'm going to stop here with some very quick conclusions. I think the key thing that I would like to illustrate is that we would like to modify the Scour equation to account for debris effects. And this is sort of a proposal that came through our industry steering committee. Who felt that the process should not be changed dramatically, but should be altered in a simplistic, in a very sensible manner to account for debris effects. And so what we are doing currently is to engage with a number of industry partners to embed this approach within Syria. This is sort of how this opportunity came about, because I approached Owen with what we are putting forward at the moment. And we are also engaging with other partners like Highways England and Network Rail as well, to see how we can put this forward within their practices or with their guidance. So I'm going to stop here. So thanks very much. If you'd like to know more about it, please get in touch with me. We also have a blog that is given there. The hyperlink is given on the webpage, on the slide. Sorry. Thank you. Thanks, Owen. I'm done.
Thank you very much, Prakash. We've had a few questions. I think there'll be a time for a couple more. So if you have got any questions you want to ask any of the speakers, please do send them in. And don't forget to make sure you indicate who you're directing the question to. So I'll unmute the speakers as the questions are directed at them. So the first one is for Rob Lamb. And the question was from Andrew Kirby of Mott MacDonald. Does the small reduction in failure probability judged by experts for the, inverted commas, with mitigation measures, close commas, cases, suggest that experts don't consider that scour mitigation measures are effective? If so, any thoughts about why that might be the case?
Okay, thanks, Owen. Thanks, Andrew, for that question. So this, for me, this was a very curious result because throughout the course of the study, in the discussions we had with the experts, the importance of risk assessment protocols and risk mitigation measures was really stressed repeatedly. So we expected that emphasis would be reflected much more clearly in their quantification estimates. So we're speculating really about what might be going on here. One possibility is that experts just aren't very good at judging uncertainties and risk. That would be a disappointing conclusion, and to some extent, it's not really borne out by the cross-check we were able to do with our independent analysis of the railway bridge failure data, and the kind of elicitation methodology that we used has a pretty good pedigree in drawing out reliable analysis of uncertainties. So I would hope that we don't need to dismiss their views. Now, it could be that there is a methodological issue here in the way that we posed the question, and that the scenarios we gave them, as I mentioned, we presented the group with a set of idealized bridge types, idealized flow conditions, and idealized assumptions about risk assessment processes. And it may be that those, although those idealizations were discussed with the group, so in a sense they were sort of accepted by the expert group as a consensus view, but there was some debate about how different types of bridge and different types of assessment protocols should be described. And it may be that we've lost something in that, and that when we pulled together the expert responses, they were making somewhat different interpretations of those scenarios that we'd set up, and we'd have to go back and do some further work on a similar group, I think, to discover whether that was the case. But the other possibility here is it may be that although they know that risk assessment and risk mitigation is vitally important, it still doesn't reduce to zero the residual risks of failure, and that's what these failure probability estimates are picking up. And that the failure probabilities here in absolute terms, in terms of an annual failure, annual chance of failure, say on a given structure, are still small. So it may just be that that our experts are saying, well, we know that there's still a residual risk, and that's an important residual risk that needs to be considered.
Okay, thank you. The next question is for Richard Williams. I'll unmute you now and I'll read the question, which is from Chris Williams, EGS. Did you consider incorporating geological metrics into the framework? Did you hear that question, Richard?
Yeah, I did hear that question. Hopefully you can hear me now. I'm unmuted. Scottish Water, within their asset inspection database, have looked at geological maps and have noted the underlying geology within their database. Explicitly within what we were doing here, I guess. The geology would be picked up on photos if it was actually a bedrock river, and we would potentially be able to identify that hard protection from bedrock if it was exposed. But beyond that, no, we haven't incorporated geology within the scoring system.
The next question will be for Danielle Zonta, and it was raised by Ioannis Soteriou. So I will read that out. Is there a way to improve the estimation of Scour with better updated equations rather than a monitoring method? Did you hear that, Danielle?
Yeah, I got the question. Yeah. Well, of course, if you have better equation, that means a better model, you probably can better estimate the quality of monitoring. However, in our project, we are not discussing the model that an agency is using for appraising, for predicting the scour depth. What we want to do is just to understand if direct information on the realization of scour can help to improve the quality of the model prediction by using updating process. But definitely, if a better model, so basically we are not studying models, we are using existing model for predicting the scour depth. What we are analyzing is the level of uncertainties of this model and the level of correlation between the variable involved in these models to see whether we can improve the performance of the model in terms of accuracy of the estimation.
Okay, thank you. At the moment we just have two more questions, one for Prakash and then another one for Richard Williams. So if you want to get a question in, we've got a few minutes of questioning left. So Prakash, I'll unmute you in a minute, but the question for you from Gustavo de Almeida is if it would be interesting if you could let us know how you have inferred scour depths based on the CFD results.
Yeah. Yeah, so the data that I showed here, most of the data is from laboratory experiments. However, from the CFD, what we have done so far is we have two approaches. One is a CFD model that directly includes sediment transport. So we have a sediment, we call it sediment foam, which is built within OpenFoam, which is an open source CFD package, and so we can either model within CFD we can model scour explicitly through sediment foam, where we use a mesh morphing method to simulate sediment transport. The other way we have done it is basically take shear stresses that are predicted from RAN simulations which don't have sediment transport. So it's a two-phase simulation with water and air, and we get shear stresses predicted around the pier, which we have basically translated into scour using existing equations that relate shear stress to scour. So that's based on empirical equations that are already around.
Okay, thank you very much, Prakash. So another question for Richard Williams, and this time from Rob Lamb. Do you think lateral erosion is sufficiently accounted for within industry guidance on scour risk?
I'll respond to this by saying when we were looking at existing industry scour risk, we found that the emphasis was very much on vertical change rather than incorporating lateral change. We're used to thinking of the position of many rivers to be static in the landscape over decadal or century timescales, which is the age that much ramp structure is approaching. Often we do need in dynamic geomorphological environments to actually think about how the position of the river might be changing upstream and downstream of a particular asset. Many rivers in the UK are relatively stable compared to more geologically young environments, and maybe I'll just refer to those examples that I showed at the very end of my presentation in the Philippines and Indonesia, where there's orders of magnitude more sediment moving through river systems each year, and a lot of geomorphological work is done by those river systems, and we do actually see significant movement within or lateral change in the position of river channels, sometimes even avulsions completely changing the pathways of rivers. So in terms of international guidance, in much bigger, much more dynamic systems compared to what we might be used to working with here in the UK, yes, I think guidance very much does underestimate there's fewer techniques to actually cope with lateral erosion.
Okay, thank you very much, Richard. We haven't received any more questions, so I think I'll draw proceedings to a close. Just a couple of announcements before you log out. The webinar is being recorded, or has been recorded, and will be available alongside other ERIIP webinars that we've done over the past couple of years on the syria.org/NERC web page. We'll send you details when they are available. Just also to remind you that there are approximately 60 projects in the NERC-ERIIP program, some of which are complete, some of which are ongoing. There's also a compendium on the syria.org/NERC web page with details of all 60 of these projects. I'd encourage you to have a look at that. Also, for the completed projects, there are case studies. I think one or two of you on the program today will have produced those case studies. We will be sending around a short questionnaire for you at the end of this. I would urge you to complete that, because working with NERC, we are trying to experiment with the different formats for these webinars. This is probably the most number of presentations we fitted into a webinar. All very interesting, but if you thought this might have been better as two shorter ones, then do let us know. All feedback gratefully accepted. So other than that, it's really now to draw the webinar to a close. The next one in the series will probably be in mid to late September, so we'll contact you about that. So thank you very much again for joining, and thanks for all the speakers and for the contributors for their presentations today. Thank you.